So let's start the review on buoyancy forces. Um, the first problem says a ball is floating in equilibrium in water, and exactly half the ball is in the water. Oil is slightly less dense than water. If you float the ball at equilibrium in oil, 1, less than half of the ball will be in the oil. 2, the ball will sink to the bottom of the oil. 3, exactly half of the ball will be in the oil. 4, more than half of the ball will be in the oil. So the idea is that the first case, what you have is, change it to a pen. In the first case, what you have is water, and so what you have is a ball which is lying exactly half in the water and half out. And it's at equilibrium, and so the idea is the weight of the ball is still there. But the idea is that that has to be exactly balanced by the buoyancy force. Okay, no big surprise. And so the idea of the buoyancy force, though, is essentially the amount of volume of water that is displaced by the ball as it's in the in the water. So it's basically just half the ball. And that's the weight of that water is the buoyancy force, which matches the weight of the ball. Now the idea is that oil is less dense, and so for a given volume you're going to get less mass, which means there'll be less weight of oil if it displaces that much. So if you take the exact same case where you've got now oil, which has less density, you have to have, since the weight doesn't change down here, the weight doesn't change, the buoyancy force has to be the same to match the weight. But the only way to do that is to actually displace a larger volume of oil than you did with water. And so as a result, the ball lies deeper in the oil, so that it displaces more oil here. But the net effect is the same. It's just that the weight of the ball has to be balanced by the buoyancy force caused by the oil. So basically less than half of the ball will be in the oil. That means that it basically is riding higher. That doesn't happen. It doesn't necessarily sink, right? I suppose if the oil was really, really light it might, but there's not that much difference between oil and water, so this doesn't happen. Clearly it doesn't mean exactly it was in the water, and so the idea is it has to sink a little bit more than it would otherwise be in order to displace the appropriate weight of oil in order to balance the weight. So, second one. A stiff metal bottle containing helium floats at the surface of a pond. If you add additional helium to the bottle, leaving its temperature and volume unchanged, the water will float, 1, lower in the water, 2, at the same level in the water, 3, higher in the water, but it will not rise into the air entirely. 4, higher in the water, it may even rise into the air entirely. Now, the problem with this is that this is trying to get exactly at the problems that are most of the problems that people have with buoyancy. The tendency is to think that somehow buoyancy is a direct result of having helium around. And so if you want to get more lift, you just put more helium into it. But the idea is that buoyancy is caused by essentially this displacement of the fluid that it's in. So the idea is that if you have a bottle that's sort of lying in the water, since it's in equilibrium, the weight has to be balanced by the buoyancy force. Okay. So when you add helium to it, what is it that you're really doing? Well, the idea is that for a certain amount of helium, there are a certain number of molecules, and so if you shove more helium into it, then what you'll end up, the only thing that you really change is the weight, and so it will, this exaggerates it, but since the weight is larger, then basically the buoyancy force has to be larger, which means that you have to displace more water. There's more weight in the bottle. So clearly, the only thing that will happen is it will lie lower in the water. It certainly doesn't stay at the same level. The buoyancy force, changes, but that's only because it displaces more water. And it certainly doesn't ride higher in the water, and it doesn't suddenly float into the air. So this is the first choice is the only one that really works. All right, third one. On a really hot summer day, you drive 100 miles and then you inflate the new $400 tires on your car to the mandated 30 psi, pounds per square inch. Because everything seems to work, you don't actually check your tire pressure until the coldest day of the year. Say it's 10 below zero. When you check your tire pressure, you're shocked that the tire pressure has dropped significantly. Your tire pressure dropped because, one, your tires became stiff in the cold and so they began to leak. 2, someone must have deflated your tires maliciously. 3, the water vapor in the air in your tires is frozen to ice. 4, the temperature of the tires has dropped significantly from the temperature they were when you last inflated them, which was on a really hot day. So if you inflate them to 30 psi on a really hot day, as the temperature drops, just like the balloon that was in the liquid nitrogen, the pressure drops. And this actually is a noticeable effect. And so it's not this, and it's not that, and it's not because of water vapor. It's just simply that as the temperature decreases, the air molecules, mainly nitrogen and oxygen, move more slowly, and so they interact with the walls less frequently. They're moving at a slower velocity, and so the force, the pressure, because of these collisions with the molecules with the walls, actually gets reduced. Four. When you make vinegar and oil salad dressing, you notice that the olive oil always floats to the top unless you shake it. If you were to fill a balloon with olive oil and throw it into the lake, it will, 1, sink because the olive oil is more dense than the water, which is why it floats on top of your salad dressing. 2, float because olive oil is less dense than the water, which is why it floats on top of your salad dressing. 3, float because balloons always float on water. 4, sink because it has exactly the same density as water. Olive oil always rises to the top of vinegar and oil. Vinegar mainly has a density of water, and so oil actually is less dense than the vinegar or the water. Since it's less dense than the water, then clearly it will float because it doesn't have to displace as much water to support the weight. So if you take a balloon and fill it with oil, then when you put it in water, it's actually going to float because it only has to displace a little bit less water than the volume of the oil, and so it will float because it's less dense. So it's this one. Clearly that one's a distractor. You can get rid of that immediately. It certainly doesn't have the same density as water, otherwise oil wouldn't lie on top of the vinegar. And clearly it's not more dense because then the vinegar would be on the bottom and the oil would be on the bottom of the vinegar. So again, this is the only one that it can be. All right, fifth one. You've seen this before. You brought home a toy helium balloon this afternoon. Already it's lost some of its helium. It's now hovering motionless at a constant height and is touching neither the ceiling nor the floor. The weight of air that the balloon is displacing, in other words, it's just sort of at equilibrium. It's floating in the air inside your room. So it's not at the ceiling. It's just basically just sort of limp there. It has a string attached to it. Everyone's seen this. And so since it's at equilibrium, that means that the weight has to be balanced by the buoyancy force, which means that the displaced amount of air has to be, which is the weight of that displaced air, has to exactly match the weight of the balloon itself. So it has to be in equilibrium. The weight of the air that displaces, meaning the buoyancy force, has to be exactly equal to the weight of the balloon. And you've seen this before. That is the end of this discussion on buoyancy forces.